Okay, I think let's start this class. Yeah. Actually, before we talk about today's class, and let's review what we have already learned in this chapter. Yeah, actually, can you recall something? Yeah. Morning. Like Yeah. Since we focus on the CT-DT-LIT system in this chapter, yeah. So we just talk about like some LIT system like properties and how to actually the very important part we talk about in last week is how to use the input and response like impulse response to represent output. Yeah, this is what we talked about last week. Yeah, actually, it's very important. You know, like the content we talked about last week is very useful for the real problems. You can see, usually you have a system. For example, you have the if you like take the robot class or some other class, you have a system. Am I right? You have the sometimes for example, you have a circuit, you have the input, am I right? You have the output, but the output it's just like the output is just specific for input, am I right? You want to use the mathematical form to represent this output, to represent this system. Yeah, you need to use the method we talked about last week. Yeah, like if you know the impulse response, you can represent the whole system using the input using like a equation. What's that equation? What's the basic thing for that equation? Convolution. Yeah, like the output is just can be represented by the input convolution with the input response. That makes sense to you? Yeah. Okay. And today we will talk about the properties of LIT systems. And before, let's try to review today's goal. And firstly, we will review the convolution sum for DT-LIT system and the convolution integral for CT-LIT system. Like then we use the impulse response, HT or HN, to determine the basic property of LIT systems, causality and stability. Yeah, actually, we talk about some properties for system. Do you remember what are those properties? Actually, this is for chapter 1. Yeah, we have talked about some, now for the LIT system, we talk about some properties for all the systems. Do you remember? Yeah, memoryless and causality and stability and time invariant and linear, am I right? Yeah, actually, this system has already been LIT system, like a linear and time invariant. But for this kind of system, we want to talk about the causality and stability to help us to know this kind of system. Yeah, firstly, let's review. Let's try to do a summary for the DT-LIT system. Actually, before we get the equation for the DT-LIT system, we try to induce like step by step. Am I right? So what's the result for this one? Do you remember? Yeah, using sampling property, it is x0 delta n. Am I right? Yeah. What's the name for delta n? Huh? Impulse. Impulse. Yeah, HT and HN is impulse response. This is impulse function. Am I right? Yeah. So, and then from this is sampling property. From sampling property, we also have this one. What's the result for this one? Yeah, xn now delta n like minus n now. Yeah, this is the sampling property. Am I right? Yeah. And from the sampling property, we can easily get this one. The xn can use this equation to represent And we talk about in the first class for the LIT system why the xn can be represented like this form. Yeah, actually in that class I think Matthew is there. Yeah, we will talk about that why the xn can be represented in this form. Yeah, because do you remember I give you an example, and this example like it's xn equal like x -4 delta xn +4 and then x negative. Yeah, because that xn is just from -4 to 2 like that. Yeah. Blah, 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 blah. Yeah, we can represent xn using this equation because the sampling property. Yeah. Okay. And from this one, then from we call this property shifting property. And then for this one, we know the name for what's the name for this one for delta n? Let me ask you again. Yeah, impulse function. And what's the name for hn? Impulse response. Why we call it impulse response? Because this impulse hn is just like the impulse function goes through a system and then give you an output like that. This is just how this system responds for an impulse function like that. Yeah, and based on this, yeah, we call it impulse response. And from this, and based on this and this, we have actually this equation. Yeah, we prove that why this equation works. Yeah, and also, what's the name for this equation? What's the name for this equation? Yeah, convolution sum. Yeah, you're right. We also use a star to represent convolution. We call this convolution sum. Yeah, and then yeah, we get the output based on this shifting property. And also from this one, we have some properties. One very important property is shifting property, which means if you have this one, and then if your like hn is delta n or delta n minus n naught, you have this one. Yeah, this we call it a shifting property. That makes sense to you? Yeah. Okay. This is for the summary of LIT, like a TI LIT system. Actually, we also have the other properties. Do you remember? Like this is shifting property. Scaling property. For the convolution, we have convolution. We have some other properties. What are those? Yeah, this is like all those properties is we focus on this week. Yeah, commutative, distributive. Yeah, like that, and associative. Yeah, those properties actually it's not that difficult to understand, but it's very useful when you like try to find the output using like input and the impulse response. Yeah, we have already talked about some examples. Yeah, okay. Yeah, then if we want to find the output, yeah, usually you will have the input signals and the impulse response. And then what you want to do is just using convolution, find the output, am I right? And for the convolution sum, actually it can be computed analytically in two cases. The first one is, the case one is xn and hn are given as short input sequences. Yeah, like if the questions or your input signals and the impulse response are very easy, like very simple. It's just like a short impulse sequences. And then you can use some properties, shifting properties and distributive properties, communicative properties, associative properties. And then you can get a easy or simple format to represent the output. Yeah, we have already talked about some examples. Yeah, you can review that. And the case two is when xn and hn are defined with a closed form. It's not just like a short input sequences. It's defined with a closed form. The key is to convert the convolution sum into the geometric series sum as two different situations. The first situation is this one. If you can like convert your like convolution sum to this form, then you can use this equation. And if you can like convert your convolution sum in this equation. Then you can use in this form, you can use this equation. Yeah, like and this is what we talk about, and you will see. And let me ask you a question. Actually, for the case one, I think you can use some properties. It's not that difficult. But for the case two, sometimes you will have two different upper bound. Do you remember? Like when we want to convert the convolution sum to this kind of equation, right? Sometimes you have two different upper bound. What should you do? Do you remember? Matthew, did you review? Yeah. Separate. Talk about discuss the different situation. Yeah, because you have two different upper bounder. You need to decide which upper bounder is the smaller one. You need to choose the smaller one. That makes sense to you? Yeah. The other question: if you have two different lower bounder, what should you do? Yeah. You also have discussed it. But for the lower bounder, you need to choose the bigger one. That makes sense to you? Yeah, because the bigger one can satisfy all the conditions. That makes sense to you? Yeah, you need to pay attention to that. Okay, this is a DT-LIT system, but let's do a summary for the CT-LIT system. Actually, for the CT-LIT system, it's very similar to the DT-LIT system. It's just like it's CT signals like that. Yeah, and then we have this. This is a water property. Sampling property. All right, we have sampling property to get this one, and then using we can get this equation. Actually, you can see you compare this one and this one. It's just like a replace integral with to replace use integral to replace some summation. Yeah, because this is like the CT signals. Yeah, and then this is the CT safety property. And similar for the similar with the DT, and this is just like the CT impulse function, and then we get the like CT impulse response, and then we have the equation for this one. Yeah, you can see what's then we can use this equation to represent it. Actually, you can see it's very similar with this one. Am I right? Yeah. Just one is CT, the other is DT. What's the name for this one? Convolution integral. Yeah, the DT, we call it convolution sum. This is integral because one is just a summation, the other is integral. Yeah, and also for this one, we have some like a property. And this is just a very useful property, like a shifting property. And this property can help us to simplify the computation. That makes sense to you? Yeah, we also can use the other like property, the associative, commutative, and the distributive. Yeah, to simplify your computation. Okay, and then for the convolution integral, actually it also can be computed analytically. According to the following two cases. The first one actually is similar, like the XT or HT are given as impulse sequences, similar like this. Yeah, very simple like impulse sequences. Then you can use properties, shifting properties and distributive properties. Not only those two, like commutative properties and associative properties. Yeah, and case two actually, when the XT or HT are given in terms of in this form, with this form, and then you need to convert your convolution integral to this form. And then if you can convert your integral, like a convolution integral to this form, and then you can use this equation. This equation, you can use it. And the similar, yeah, the key for this one is to remove the unit step. This one, by changing the boundaries of integral to make the integration computable. Yeah, actually it's very similar. This one is just like the sum, and this one is just the integral. Integral. Yeah, that makes sense to you. And also, this one also has the problem like the boundary thing. If you have two different upper boundary, you need to talk about that. Which one is the smaller one? If you have two different lower boundary, you need to discuss which one is the bigger one. That makes sense to you? Yeah. Just remember that. This is what we have already learned for the LIT system. Yeah, because you can see if we can use those things to get the relationship between the input and output, we can represent this system. Am I right? Yeah. So then let's talk about the properties for the LIT system. The first one is the causality of LIT system. Actually, we learn different properties: causality, memoryless, stable, and for the LIT system. Let's talk about if it is causal or not causal. Yeah, actually, the output of a causal system. Let's try to review what is if the system is causal. What's this system look like? It depends on the present and the past time. Am I right? Yeah. So which means the output of causal system depends only on the present and the past values of the input to the system. Am I right? So let's try to review this is the CT-LIT system. Am I right? For the DT, actually, it's a similar thing. Yeah, this is the equation for the CT-LIT system. Am I right? So for this system, we can rewrite this equation to this one. That makes sense to you? Yeah. Negative integral to infinity to t. Here is t to positive infinity. If you add them together, it's just the same one with the original one. That makes sense to you? Yeah. And then let's try to observe. For this one, when we discuss the properties for the system, we talk about that you only focus the input signals and the output signals. Other things you don't need to mind, am I right? So let's try to observe this equation. For this equation, x tau, this is input signal, am I right? Tau, what's the tau? The tau's range is from negative infinity to t, am I right? What's t? Actually, t is the present time, am I right? So for this part, the tau always smaller than t, am I right? So what does that mean? Which means this part is the causal part, am I right? Because the input is always the present or the past time signal. That makes sense to you? Yeah, so which means this is the causal part, am I right? Yeah, but for this one, the tau's range is from t to positive infinity, which means this is involves the future time. That makes sense to you? So, which means this is non-causal part. It is because it involves the future signals. Am I right? Yeah. So let me ask you a question. If you want any LIT system to be a causal system, what's the condition? Yeah, this is any LIT system. Am I right? Yeah. So if you want this LIT system, it's causal. What's the condition? What's the condition? Huh? Only past or present, am I right? So which means this one is it can be here, am I right? But this one, I don't like this, am I right? If your system involves this part, it means it will involve future signals, am I right? So which means I want to remove this part. That makes sense to you. So which means, yeah, if you want this LIT system to be causal, this part must be 0. That makes sense to you. If this part is 0, then this LIT system will be causal. That makes sense to you. Okay. Then yeah, which means the signal, the input signal is here. We cannot guarantee it is 0 or not, because signals is just like some any signals we can use them, right? But if this is just like the impulse function to the the impulse response to the impulse function. The impulse function is fixed, am I right? So this one actually is fixed. It will not change. That makes sense to you? Yeah. So if we want this LIT system is control, which means this part is 0, then we can remove this one. That makes sense to you? Yeah. If this part is 0, which means like t negative tau, if tau greater than t, this part is 0, then it will be correct. That makes sense to you? Yeah, this is just the condition. And then we can change this one to this one. You know why? You know how? Do you know how? Now why? Yeah, let me. Yeah, we want this system is correct, which means T minus tau equals 0 when t greater tau. Am I right? That makes sense to you. Then we let this part is f. Like we just use f to replace this part. Then hf equals 0. Like t minus tau. If the tau greater than t minus tau smaller than 0, am I right? From here, am I right? So this is f, am I right? Which means f should be smaller than 0. Yeah, if we use f to replace t minus tau, we can have this equation, am I right? Actually, ft is a similar thing. It's just a variable. That makes sense to you. So you can absolutely write this is ht equals 0 when t smaller than 0. That makes sense to you. See, that's the reason why here we can use this equation to represent it. That makes sense to you. Okay, then it will be easy for us. If ht when t smaller than 0, like ht equals 0, then your LIT system will be causal. That makes sense to you? Yeah. Okay. Then your causal LIT system, you can represent like this. Yt equals this one. And if you have this condition, at equals 0 when t is smaller than 0. That makes sense to you? Okay, let's try analyze the causality of LIT system more deeper. Yeah, we can like rewrite any LIT system using this equation, am I right? And then you can see this part just involve past signal, am I right? Tau smaller than t. We call this a causal part. Actually, if you use a similar method here, you will know this part will greater than 0. And for the second part, this is the future. You will know like this part will smaller than 0. Am I right? Yeah. And then you can see here, this is ht. We just talk about ht here. Like for ht, this is just the causal part. This is the non-causal part. All right. We call that part is causal part, and this is non-causal part, which means yeah. And for the xt and yt, and like the ht, for the ht, you can see this is just the present time, all right? And this is this part will like involve with xt, past xt, am I right? Yeah, this part, this like a causal part is involved with past part, am I right? Yeah, and this part involved with like a future part. Yeah, based on the equation. That makes sense to you, am I right? Yeah, this part you can see it will combine with the future part, and that part is this one. We will combine with past part, am I right? And this is just a present time. But all the time, all the like part will relate to the present time. You can see the yt, no matter your signal is whatever your signal, but your output is always present times output. Am I right? Yeah. So what does that mean? Which means if you want your system is color, your H, this part will be 0. Which means if you draw your HT, this part will be nothing. Only this part have some value. That makes sense to you. And then your system will be color. That makes sense to you? Yeah. Okay. Did I speak this like opposite? Which this part should be nothing. Am I right? And this part should be have some value. Yeah, because this part is involved some color part, and this part involve non-color part. If you want your like a system color, this part should be nothing. This part should have some value. Yeah, that makes sense to you. Okay, then let's have a like a look at example. This one. This is our HT, and this one. If you draw your like HT, what is look like? What is look like? What it looks like? Yeah, this is T. This is HT. How it looks like your HT? The first one, the first part. What's the when you draw this one? What's that? Delta T minus 1, which means only when T minus 1 equals 0, it has value. Am I right? Which means here 1, it will have this 1, have this value. That makes sense to you. Otherwise, it will now be 0. And for the next one, delta T, if only when this T equals 0, it will have the value. Am I right? So it will like this. Am I right? And the third one is only T plus 1 will equal 0, it will have value. Negative 1. It's like this, am I right? Yeah, so which means it has the present part. For the HT, it has a color part. This is color part. It has a non-color part, am I right? So, yeah. Oh, sorry, this is negative. There is a negative. Yeah. That makes sense to you? Yeah. Okay. And then our XT. Yeah. Which property you can use? If we want to have the output, which property you can use? Huh? Distributive. Yeah, am I right? Yeah. You can see. You can have this one, am I right? Yeah. Like this distributive and shifting. Am I right? Yeah. Let me write it. You can see the YT equal XT, HT, am I right? Equal XT convolution with like delta T minus 1 plus delta T minus delta plus 1. Am I right? And then distributive, 然后 you just convolution with delta T minus 1, like plus xt convolution with 2 delta T minus xt convolution with delta T plus 1. Am I right? But then for each atom, you use shifting property. Am I right? Then you can get this one. Am I right? Yeah. Okay. Yeah, for this one, which means that for this equation, for this output, this is color part. Am I right? Actually, this is color part. This is just a past atom. Am I right? This is the present atom. This is the future atom. If you have this atom, which means your LIT system is now color. That makes sense to you? Yeah, this is just try to analyze the correlative of LIT system. Okay, let's check an example. So, how to decide the correlative of the following DT system? Yes. How about this one? This is HT. Is if you're like impulse response, yeah, you can see for any LIT system, if you want to decide this system is color or not color, It now depends on xt. It's not depend on your input signal. It depends on your input response. Am I right? So you just check your input response. If your input response has something in this part, then it is not choral. That makes sense to you. If it is only have this part, it is choral. So let's check about this one. How about this one? It is choral. Your system is choral or not choral? Yeah. Firstly, let's talk about what's your n for this part un minus 2. What's this? Un minus 2. Yeah. What's this? 1, 0. If it is n minus 2 greater or equal to 0, it will be 1. Otherwise, it will be 0. Am I right? Which means that n greater or equal than 2, it will be 1. Am I right? So, which means your n should from 1 to. And point 5 n, which means it will be just like this. Am I right? So it's just a similar like this. Am I right? Yeah. So your system is choral or not choral? Am I right? Yeah, you're right. Because you only have this part. Am I right? Yeah. So your system is choral. And how about this one? How about this one? What's the n? Yeah, actually, you can see you don't even draw it for the un minus n plus 1 plus 2. Like which means if you have negative n plus 2 greater or equal than 0, it will be 1. Am I right? Which means n like smaller or equal than 2. Am I right? So which means your value should 1, 2, 1, 2 will be similar like this. Am I right? So what is choral, not choral? Not choral. Yeah, that's right. Because you have something here. Am I right? Yeah, if you only have something here, it is choral. Yeah. Okay, let's check this one. How about this one? Actually, it's similar. It's just a CT. CT is this one. How about this one? Just try to find what's your T. What's your T's range? Am I right? For this one, what's your T's range? U T minus 3, which means your T should T plus 3 is greater or equal than 0, am I right? Your T greater or equal than negative 3, am I right? So is this choral or not choral? Yeah, it is not choral. Only this part you have value is choral. Otherwise, it is not. Even you have just a little, it is not choral. Yeah, because you have something in this part. Okay, how about this one? How about this one? What's T? What's T's range? What's T's range? U negative T, which means your negative T greater or equal than 0, right? T is smaller or equal than 0. Am I right? So what is choral? It is not choral, not choral. Yeah, it is not choral. Oh, absolutely not choral because it's only like this part value. Okay, other question so far? Okay. Let's try to check the stability of our system. What's the if a system is stable, what does that mean? Do you remember? Yeah, stable like a like a bounded input result, bounded output. I'm right. So a system is stable if every bounded input produces a bounded output. Yeah, like this. Yeah. If we want to, which means for the like LIT system, yeah, the DT and CT is similar thing. Which means if we have the bounded input and then we have bounded output, it will be stable. Am I right? So let's try to talk about that. Yeah. Like we just try to improve. This is bounded output, am I right? So this is output, am I right? So we just use this one to replace this part, all right? And then we can have this one. What's the property we use here? From here to here. Commutative, change the order, am I right? Yeah, when we talk about you change the order, it's the same thing. Yeah, when we talk about the convolution, it's the same thing. Yeah, and then it will be smaller than this one. It's just like a fundamental thing. Yeah, because you can see, if you sum some items and then do absolute, which means it is much smaller than you absolute first and then sum. That makes sense to you? Yeah. Have you ever heard this before? Yeah. Let me give you an example. For example, you add use salute. This is absolute. You answer negative. Sorry. This is -2 plus -1 plus 1 plus 0 plus 2 plus 3. And it must smaller than, it is smaller than like absolute -2 plus absolute -1 plus 0 plus 1 plus absolute plus. All right? That makes sense to you? Yeah, you can see if you use absolute firstly, which means it must be positive number, am I right? But if you use this one, you cannot guarantee this the every item is a positive number. It might be negative, am I right? It will become smaller. So this equation must be smaller than this one. That makes sense to you? Any question? Okay, and then we know like the input signal is bounded, am I right? So which means it must be smaller than B. B is this like here big number, but the B is just the maximum number for X the signal input signal, am I right? So this must be smaller than this one. Okay, then which means it must be smaller than this part. What does that mean? What does that mean? Which means if this part smaller than infinity, and your output is bounded, am I right? That makes sense to you? So which means if your DT or CT signal is stable, or DT or CT system is stable or not stable, which means your impulse response, if your impulse response is infinite, is bounded, and then your LIT system is bounded, is stable. That makes sense to you? Yeah. Okay. For the CT, it's a similar thing. Yeah, it's just like using this equation, which means for the DT-LIT system, if your like impulse response like can make this work, and your LIT system is stable. If your CT-LIT system is stable, which means this condition will work, is successful. That makes sense to you? Okay, let's try to how to determine the stable from the impulse response. Yeah, we have already talked about that. For DT-LIT system, you can see if your impulse response equal this one, if you observe our examples, your impulse response usually is just similar like this, am I right? So which means this is a right-sided. So it's we call it a choroid part, am I right? And this is a left-sided, it's a non-choroid part. Yeah, but the system, the LIT system is stable or not stable. It's not related to the choroid or not choroid. It's two different things. And even this system is stable, it can be choroid, it can be non-choroid. Yeah, it's not related to with each other, stable and choroid. Yeah, choroidality. Yeah, so this is for the LIT for the DT-LIT system. This is the choroid part. This is the non-choroid part for the impulse response. And what's the condition for the LIT system is being stable? Which means if your like we know like if your impulse response like works for this equation, it will be stable. Am I right? We have already proved that. That makes sense to you? Yeah. So which means if your DT-LIT system, the impulse response looks like this, which means if your A smaller than 1, like the absolute is smaller than 1, and the B, absolute B, greater than 1, which means your system, your like LT system is stable. Do you know why? You can see if your A is smaller than 1, like absolute smaller than 1, which means your this part will converge to 0. That makes sense to you? And if your B greater than 1, this part, which means your this part will converge to 0. Which means your like HK must be smaller than infinite. Because this one. That makes sense to you? Yeah. And for the CT, like system, usually you will represent your response impulse like this. And then for this one, actually it's a similar thing. Yeah, this is the right side. And if A smaller than 0 and B greater than 0, and your this LIT system will be stable. Why? Because it's a similar thing. Yeah, if it will be like this, converge to 0, and then your this condition must be successful. That makes sense to you? Yeah, this is how to determine the stability from the impulse response. Okay, let's try to take some examples. Please consider the chirality and stability of the ideal delay system and the accumulator. Okay. Sorry, I think I give you one. That's fine. Let's try to check this one. How about this one? What's let's try to check color or not color. Yeah, the N now must be greater is a positive. Color or not color? Yeah, let's yeah, it is N minus N now, right? If N now greater than 0, which means it will must be this one, right? Or this one. That makes sense to you? Which means it is color. If N now like greater than 0, smaller than 0, which means it is here. So the color or not color depends on N now, am I right? Yeah, let's check the stability. If this system is stable, which means this one must be smaller than infinite, am I right? Which means what's the value for this one? Yeah. Actually, for this delta, negative N now, like this is Hn, am I right? Yeah, it no matter Hn is what, it must only one this one, am I right? Only one value in specific N naught, am I right? So if you add them together, it must be 1, am I right? So it is smaller than infinite, so it is stable or not stable? Yeah, it is stable. Yeah, how about this one? Yeah, it's the color or not color is similar with this one. Am I right? Similar with what we have already talked about. And for this one, it is also 1, am I right? So it is smaller than infinite, it is stable, am I right? Yeah, I just, yeah, I think I just opposite that. Yeah, so it is color and stable. That makes sense to you? Any question? How about this one? It is color or not color? Yeah, it is color because n must n greater or equal than 0. It has something. Am I right? And how about the stable? Yeah, it's not stable. Yeah, because the UN is just like this. Goes to infinity. Am I right? Any questions so far? So it's color and not stable. Any question? Okay, how about this one? Actually, it's the same thing, similar thing. Am I right? So it is color not stable. Am I right? Okay. Let's try check more example. Yeah, this one is more complicated. And for this one, let's try to, how about the, it is stable or not stable? Let's try to check if it's stable or not stable. For this one, what's the range for, if you want to check the if it is stable or not stable, you just need to check what's the range for n, am I right? If n like involves some value smaller than 0, it will not stable, am I right? So for here, well, what's your n range for n, which means only n plus 2 greater than equal than 0, it has value, am I right? Which means n greater or equal than -2, it has value. So what is it is color or not color? Yeah, it is not color because n involves some value smaller. And let's try to check if it is stable or not stable, which means you need to find like a negative, positive, like a Hn absolute, if it is smaller than infinite or not, am I right? So let's try to check effect. This converge if limited. This is smaller than 1. Then it is converges. Yeah, it's some mathematical fact. Yeah, and then which means if you want to like find this, if this like because it's the start from -2 to infinity for this one, right? But it's similar. That makes sense to you? Yeah. So we need to check if this equation, put this equation to here. If it is limited to n goes to infinity, it is smaller than 1. It will be called stable. Am I right? So similar. We have this into this equation. Am I right? And then we have this equation. Am I right? So actually, if this goes to like infinity, it will be removed, and then you will have this one. So which means this one will be smaller than 1. And so this, which means this one is stable. That makes sense to you? Okay. Yeah, you just try to, this is a mathematical fact. Yeah. Okay. This is non-color but stable. Okay. And how about this one? How about these two LIT systems? The first one, it is color or non-color? Yeah. The second one, actually, I think it's similar. Am I right? It's color. Am I right? And they are not just anything. They are the impulse response from the LIT system. Yeah. This one you can see is we just talk about it. It's not system input system. It's not output. It's not system. It's just an impulse response. Am I right? So which means for a system, if you can like tell the situation for the impulse response, then you can tell your system is color or not color, your system is stable or not stable. Okay, and then so if we want to decide if it is stable or not stable, we need to check this equation, am I right? So then we this is some equation we need to know, and then we just put the equation here. It will go to infinite. Yeah, which means this is not stable. That makes sense to you? And for this one, yeah, we call it a harmonic progression. Yeah, and this is color and unstable. And for this one, actually, you can see you will have the thing, but here is n squared, 1 over n squared. And if you just use this equation, you will find it is stable. Yeah, any question? Okay. Yeah, there are some homework determine the causality. Yeah, for the causality, I think it's easy. You just check if your n or t is if it is involved some value smaller than 0. Am I right? For stability, you need to use this equation to check that. Am I right? Okay, I think yeah, we will go through these problems next week, next class. Yeah, so we just talk about how to tell the LIT system is color or not color, is stable or not stable. Yeah, any questions so far? Okay, that's great. Yeah, let's continue to talk about next class.